Okay, hello Analysis 1A, welcome back. This video is going to be in place of class on Monday and Tuesday because apparently we're not having that. So here we go. Let's just push on with our learning. Things are going kind of slowly, but we are really learning calculus. So far we don't have much. Basically at this point we can differentiate polynomials and power functions. Well, it's time. Our book crams this all into just one section. I would like to find the derivative of sine. Alright, yeah, how can we do this? There are many different ways that we can do this. First, perhaps we should just draw a picture. So let's go. So I have a picture of the sine function. What does it look like? Well, it's actually very important that we are careful and that when talking about the derivative of the sine function, we make sure that we are in radians. Because actually everything that we're about to do applies only in radians. Not only that, but I'm going to try to draw my sine function sort of accurately, and by that I mean really drawing it on kind of a square grid. So if that's 1, then you know that makes 3 about maybe over here. So that's pi. This picture is now way too big. Well, okay. I guess that's about 3. Sure. And then 2 pi is like over here. That's sort of almost surprising. But okay, so what does the sine function look like? It kind of has this look like this. I'm kind of trying too hard now to do a good job. And then sort of a little bit of that. And then, okay, I guess that's just what sine looks like. Okay, and then negative pi over 2 is going to be over here or something. So we're talking about this. All right, well, great. That's the sine function. Okay, so that's pi over 2, 3 pi over 2, and 2 pi. And now I would like to know what the derivative of this function is. In other words, I would like to find a function which tells me at every single point what the derivative of sine is, what the slope of the tangent line is. Alright, well, first, maybe the thing to do is just to guess. And if you guess right, then you already know the answer, and that's great. So, in other words, let's just look at this sine function, look at the slopes of the tangent lines, and see what they are, and then maybe I'll just suddenly know the answer, because at the moment, I don't know. Okay, well, starting over here at 0, I don't know about you, but if you draw the slope of this, if you draw the slope of this tangent line in here, to me, that line, especially if you draw it accurately, that looks a lot like the slope might be 1. And, okay, when we do this lecture live in class, at school, many people are like, that looks like 1 to me. And yeah, the more accurately you draw the graph, the more it does look like 1. Is it 1? Well, actually, this problem can be solved. Because what would it require to find the derivative at 1? Well, I can just use the definition. The definition of the derivative, and maybe now I'll even introduce like a new symbol. So the derivative of sine, but at x equals 0. So that kind of just means evaluate this at x equals 0. Well, just is the limit as x approaches 0 of f of x minus f of 0 over x minus 0. I don't know if I need to keep writing that out, but that's just the general definition of the derivative of a function at 0. So for the sine function specifically, then this is sine x minus sine 0 over x minus 0, but then sine 0 is just 0. And so this whole thing just reduces to the limit as x approaches 0 of sine x over x. Okay, so if you followed that, and this limit we know. So this limit we did 2 weeks ago, as a kind of a preview, I call this the most important limit in all of calculus. This actually just establishes something that I didn't mention at the time because we weren't really solving tangent line problems yet. But effectively, what the limit as x approaches 0 of sine x over x is saying is that the derivative of the sine function, I'll erase this question mark, is in fact 0. It is in fact 1 at x equals 0. And in some ways, when we discussed this previously and talked about why this was something kind of that was important that I cared about, what it did was express the fact that that when x is almost 0, sine x is approximately x. That sine x is pretty much x for very, very tiny values of x. Of course, these two are saying the same thing. But this is kind of also saying the same thing in a slightly different way. If you think of this line now, this red line as being the function y equals x, then what it's saying is if you zoom in on the origin here, that these functions are pretty much the same. That the ratio between them is 1, that they're pretty much the same, that the line y equals x is the tangent line. These are 3 or 4 different ways of saying the same thing. Okay, so what have I accomplished? My light switch is kind of in the way, but basically what I've accomplished is that the derivative of the sine function is at 0 is 1. So let me put a little dot here at 1, and let's move on and try to find the derivative at some other places. So boom, 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 boom. Okay, well, without spending too much time on this, I mean, just come on. Up here we know that the sine function has a relative minimum. So what's the slope of this line? Well, it's going to be a horizontal line. Of course, its slope is going to be 0. In other words, whatever the derivative of the sine function is, in general, I still don't know yet, but at pi over 2, it's 0. A lot of background noise going on here. Okay, what about at pi? Well, I can also draw at pi, and I see that at pi, the slope is -1. Because just kind of by symmetry or something like that. And so here at pi, this is -1, and at 3 pi over 2 again, this is 0. This line has slope 0. And okay, this is supposed to be, assuming you've managed to avoid accidentally learning about this, this is supposed to be like kind of an amazing moment. Of course, this is now back to being 1 because this function is periodic. And so by just kind of like looking at the picture and thinking about it and drawing tangent lines, I have already concluded that the derivative of the sine function must be a function which at these various places, pi over 2, pi, 3 pi over 2, and 2 pi, have these various values. And okay, there's a well-known function which does this, and it is cosine. Alright, so I'm just going to conjecture right now that, and this is the kind of thing you could have, just done yourself, this is a sort of guess the derivative by sketch, that the derivative of sine is cosine. In fact, this is true. Let me erase all of this maybe now, and we'll just quickly prove it. Okay, well, yeah, let's go. So, I don't know, I thought that was fun or something. I don't know about fun, but it's better to sort of discover something on your own, or at least to see a way that you could have easily discovered it, instead of just jumping right into the proof. And, alright, the proof we're going to give 2 different proofs. We're going to give kind of a, that was proof by experiment. This is proof by formal definition of derivative, and then we're going to do a proof, a geometric proof. So, okay, what's the sort of most kind of mindless way to go about this is to just use the definition of the derivative. So what is this? The definition of the derivative, in general, if we're trying to do this kind of all at once, is the limit as h approaches 0 of f of x plus h minus f of x all over h. And so I need to write this, so this becomes, for me, sine of x plus h minus sine x all over h. And here we find ourselves in a situation where it's basically not possible to make any kind of progress via any sort of algebraic manipulations. After all, sine is not an algebraic function. There's no kind of conjugate multiplying or anything like that, which is gonna give me any progress. There's really only one thing to do, and that is to try to split this up in some kind of way. Notice, the same thing happened when I was trying to do the power rule. When I was trying to do the power rule, I had this in my numerator, and I kind of just expanded. Well, here once again, I just need to expand. Oh man, very loud down there. All right, so this becomes the limit as h goes to 0 of, well, I'm just going to use the formula for sine of a sum. And the formula for sine of a sum is sine x cosine h. This is like kind of an essential piece of background pre-calculus knowledge. Sine x cosine h plus, what am I doing? Sine cosine and then plus cosine x sine h minus sine x all over h. Okay, this is now getting even worse because I have sines and cosines and x's and h's. It's potentially, quite confusing. But look for sort of pattern and structure and use your sort of experience that you have on this matter. In fact, we did a problem like this towards the end of the limits unit. I notice something. What do I notice? I notice that sine h over h is lurking here in the middle. And we're taking the limit as h goes to 0, so h is a very, very tiny number. Well, this is our limit again, merging, that limit that I called the most important limit in all of calculus. And so somehow I want to extract the middle term alone from this fraction, and I think this is going to go to 1, and that's going to be kind of nice. So let's do that now. Let's split this into two pieces. Let's split this into the limit as h approaches 0 of cosine x sine h over h, and the limit as h goes to 0 of, well, if I take that middle term out of the fraction, then this is sine x cosine h minus sine x over h. Okay, so what just happened now? Okay, yeah, I just did I split the fraction up using rules of fractions, and I applied the rule that says that the limit of a sum is the sum of the limits. Well, now I think we see why this is so good. Okay, there's another little bit of sort of sophistication that you have to have here. You have to realize that we're taking the limit as h goes to 0. So h is the thing that's changing. Cosine x is kind of like a constant with respect to this limit. And by that I mean, cosine x is just not changing here. So I can just pull it right out of this limit. So hopefully you're comfortable with that. So I'm going to do that. Pull out the cosine x, and I get the limit as h goes to 0 of sine h over h. And, okay, what about over here? Well, here also I can kind of do something. What is it that I can do? Well, I can certainly factor a sine x out from the numerator. Maybe I'll do that in just kind of in its own step here. So, and then I get cosine h minus 1 over h. All right, and now if you're sort of a very good calculus student or something, you will realize that this also is a limit that I have seen before, right? This limit is 1. This is this thing I call the most important limit in all of calculus, and so that's why I get cosine x over here. But what is this? This is another important limit. It is in fact 0. And okay, if you forgot why, I'll sort of show you one more time. We can multiply by the conjugate. So this is cosine h plus 1 over cosine h plus 1. And okay, I'm going to do sort of two things now. One is, once again, since I'm taking the limit as h goes to 0, sine x is a constant. And so I can just pull that sine x out. But now this becomes the limit as h goes to 0 of cosine squared minus 1, which is actually negative sine squared h. I think I can do that all in one step. And there's an h here still as well. Okay, and why is that? helpful. So cosine squared minus 1 is definitely a negative sine squared. Well, finally then, I can write this as sine x times times, maybe we'll do it like this. The limit as h goes to 0 of sine h over h times the limit as h goes to 0 of negative 1 over cosine h plus 1. So now I apply the limit of the product is the product of the limits to split this limit up. That's if you forgot this fact over here. So what have we just showed? Well, this is going to 1, and this is going to negative 1 over cosine of 0 is 1. So this is going to negative 1/2. And if this is going to 1, sorry, what am I doing? This is going to, I forgot a sine h. Oops. Okay, back up a second. I made a sort of bad algebra thing here. Sorry, this is sine squared here, so one of the sines goes here and the other one goes here. There we go. So this is going to negative 0 over 2. Okay, so this limit is going to 0, and so the product of 1 and 0 is 0. You could have just answered that immediately up here if you already had sort of memorized that fact. Anyway, this whole thing then over here is going to 0, and then the final answer to this problem is just cosine, because everything else disappears. Alright, this is a kind of amazing and incredible fact that the derivative of sine is cosine. This proof, however, is, I don't know, fine. This is basically the exact proof that's in the textbook. This is the exact same kind of proof you can find in a million different places all over the internet and in different textbooks. So nothing special about my version here. It's nice, but it's annoying, difficult, kind of boring, and seeming to involve like a lot of algebra. The one thing I'll mention before I erase this board is that this limit is playing a sort of crucial role in this proof. And why is this limit 1 again? Well, I won't go into the proof we gave a couple weeks ago, but I will mention to you again the proof that we gave back in Pre-Calc C. And the proof we gave back in Pre-Calc C was simply that the sine function takes as its input, okay, I guess I'll call this h. So if this is h, then this is sine h. So built into this limit being 1 is the geometric definition of sine as the height. But what I want to mention right now is that built in sort of in a crucial way to the proof of this limit is the fact that the input to the sine function is the arc length on the unit circle. In other words, I am using radians, and in fact I must use radians when I do calculus. The entire setup here assumes that I'm doing trigonometry in radians. Only in radians is it true that the input to the sine function is the length of the arc on a unit circle. And so the fact that I'm using radians is built into to this setup. It's built in, therefore, to the proof of this fact of this limit being 1, and therefore it's built into this derivative, this function cosine as being the answer to the derivative of sine. And in fact, if you try to do calculus like in degrees, you will find that the limit as h approaches 0 of sine h over h is not 1. In fact, it's some disgusting thing like pi over 180 or something like that. And you can even, maybe I'll do it right now, for one time ever, just to say that you should never do it again. If you try to do calculus in degrees, then that's 1, but this all the way over here is 360. That's probably, not even close to being accurate. And so, maybe I'll be even more sort of ridiculous. So this is why we don't do calculus in degrees, because calculus asks for the slope of the tangent line to the curve, which is really asking, about a particular slope of a particular line, and so it really only makes sense to visualize that line in a square grid, so to speak, like I mentioned at the beginning of this video. Well, I hope you see now that if that's 360, that's 180. I'm not sure how good this picture is. But now it's going to be like, you know, sine is going to look like this or whatever. And the slope of that line at 0 is no longer going to be 1. The slope of that line is actually going to be something really stupid like, yeah, pi over 180 or whatever. Okay, so there we will never speak of degrees ever again for the rest of this class. And one of the reasons why we kind of banish degrees in pre-calculus from discussion is because though it's useful for things like physics, it's just the wrong way to do trigonometry when it comes to doing calculus. If you do calculus correctly in radians, you get these nice pretty formulas. Okay, oh my god, this is going on too long. I'm going to erase this proof. Okay, my child is just screaming. I hope this is not coming through on the video, but I fear it may be. That's screams of joy going on down there. Good. Okay. Yeah. Oh, maybe I should mention, just really fast, that we could also conjecture what the derivative of cosine is. So maybe I'll just do that. But let me do it like super fast. Well, okay, I draw a cosine in radians. So what does it look like? It looks like that, I guess. And okay, so if that's the derivative of cosine, then you know cosine is just sine shifted over or whatever. And so the key places to look are at 0, where the slope is clearly 0, at pi over 2, where the slope is -1, Jean, and at pi, where the slope is 0, at 3 pi over 2, where the slope is 1, and then again at 2 pi, where the slope is 0. This is just the cosine function. Well, then down here I will make a picture of the derivative of the cosine function. This is the exact same thing I did with sine, just going a lot faster now. Okay, well, 2 pi, picture is a little bit crappy, but that's fine. 2 pi, and here's 1, and here's -1. Well, what do we think? Well, it starts out at 0, boom. Then the derivative is -1 at pi over 2, boom. Then by the time I get to pi, my derivative is 0 again. And by the time I get to 3 pi over 2, my derivative is back to being 1. And by the time I get to 2 pi, it's back to being 0. And so if I'm willing to kind of guess, well, it's really just the same shape, so it kind of has to be, sort of sinusoidal. We get this kind of just like amazing, I think it really is kind of just like an amazing fact that the derivative of sine is cosine. Well, I think I'm ready to, okay, maybe I'll just say it right now, right? So fact, the derivative of sine is cosine, and this we proved pretty carefully, and the derivative of cosine is, just look at it, negative sine. This is sort of amazing, and if you've been following everything I've said so far, I suspect you don't even really understand or appreciate, you know, what this means or why this is true or anything. So this really kind of telling me that at every single moment on the graph of sine, that's kind of what this is saying. At every single moment on the graph of the sine function, yeah, that the rate at which this function is changing is determined by the cosine function. And, okay, at every point on the cosine function, the rate at which it's changing is the negative sine function. And so you have this, okay, you know what, I'll stop there. Okay, good. A proof. This is calling out for a proof that shows understanding. So I gave a proof that is also in your book, which is very sort of dry and boring and algebraic. But really, calculus is about geometry, and it's kind of a shame in some ways that calculus has been kind of taken over by all of this sort of tedious symbol pushing. The good thing about symbol pushing is that anyone can do it. The bad thing about symbol pushing is sometimes you can just push a whole page full of symbols, and the whole page is over, and you just have no idea like what you're even doing or why or how or what it all means. So I crave giving you the like 17th century, 18th century feeling of doing calculus, of really discovering true sort of like facts about the world or whatever. And you know, let's go. Okay, so let's revisit a couple of the things we've already learned, but from a geometric perspective. So what is the derivative of x squared? You have been told. Well, it's 2x. Okay, you can prove that with a simple limit argument, and you know it's certainly true, and maybe that's all there is to it. But okay, right? Built into this x squared, you know, is the word square, right? That's just because x squared means or meant to people for thousands of years, you know, something involving squares. What does x squared mean? Well, it's the interpretation of x squared is the area of a square with side length x. And so you might think, and I in fact believe, that this theorem, instead of being a theorem about polynomials, whatever they are, this is a theorem about squares. This is telling me something about squares, something sort of deep about squares. What is it telling me about squares? Well, it's telling me about the rate at which this square is increasing in area. Let me back up. X squared is specifically the area of a square with side length x. Okay, here's a square with side length x. Its area is x squared. What does it mean to take the derivative of x squared then? It's asking for the rate, the speed of the area of this square, or the rate of change of the area of this square. What this problem is really asking, this left-hand side of this equation, is if I take a square, at any given moment, suppose the length of one side of that square is growing, how fast is the area of that square growing? And so now we get this kind of sort of deep way of thinking about differentiation. Differentiation measures the rate of change, the instantaneous rate of change. In other words, if you make this, if you let x become a tiny bit bigger than it already is, then what effect does that have on x squared? Alright, well, we just do it, man. We just let this square be a tiny bit bigger. So just draw now a sort of infinitesimal increase in the square. In other words, take my square of side length x, and perhaps I'll even color it in like a sort of a shaded, you know, sort of green thing there. That's my x squared square. That's my square of sine length x. Let it be a tiny bit bigger, and what happens to the area? Well, now the length of this square is no longer x, but it's a little tiny bit more than x. Call it delta x, where we think of delta x as infinitely small. Okay, and then this is also infinitely small. And what do we got here? Well, we got a new square, which is a tiny bit bigger. How much bigger? Well, you have some options here. I can just count how much bigger it is. It grows in sort of three pieces. There's the kind of this piece, the this piece, and the this piece. And what can I say about this piece? Well, this is x times delta x. So in other words, the area of this extra little sliver here on the side is a rectangle whose area is the side length of the square times this infinitesimal increase. And what is the area of this piece here? Well, it's x times delta x. And it is, again, just the length of the square times the infinitesimal increase. And then what is this thing? Well, this is like delta x times delta x. And I have some sort of deep feeling now that that's just too small to be worth caring about. in other words, this delta x thing, this is what they would have called an infinitesimal. What's an infinitesimal? An infinitesimal is just an infinitely small number. Well, if you multiply an infinitely small number by x, that's still something significant. And if you multiply an infinitely small thing by x, that's still significant. But the product of two infinitely small things is basically insignificant. And, okay, so I claim, therefore, that the 2x that appears in this formula is really just the area of these two little blue things sticking out of the side of this square. And if you want to see some sort of justification for this, well, okay, you can do it. But if you start to do some algebra, then you're sort of doing algebra, not geometry. But what is the kind of change in the x squared function with respect to a change in x? That's kind of what we mean when we take the derivative, right? If I change delta x by a tiny, tiny bit, what happens to x squared? And the answer is that the square gets a tiny bit bigger. How much bigger does it get? X times delta x, the first blue rectangle, plus x times delta x, the second blue rectangle, plus delta x times delta x, the little tiny square in the corner. And sure enough, if you divide by delta x, then what do you get? You get 2x plus delta x. And this is basically insignificant and disappears. Okay, so this is how people did calculus. Once upon a time, this is how Isaac Newton did it. I don't think he did proofs with limits. I mean, he definitely didn't do proofs with limits. He just had a feeling that that this little extra corner is just too infinitely small to even matter. And they just kind of drew pictures like this, and sort of there it is. Okay, wait. There's more. So what is this saying? On some deep level, what this is saying is that for every sort of millisecond that goes by, the square gets bigger by 2 times whatever the side of that square is. And the two x's are these two x by infinitely small rectangles. I'm kind of just repeating myself now. Another thing you can do is you can just another thing to do if you've never seen the product rule before is just to draw a square with side length like 3.1. Okay, so let this be, so this is now not even calculus, you might say. So let this be 3, and let this be 3, and let this be 0.1. So like, 1/10. And then this over here is like 1/10, right? Well, okay, what do we have? That's 1/10. What we have here is a square of area 9. And what is this? Well, this is like pretty tiny, right? This is going to be like 9/10. And no, sorry, 3/10. Maybe I'll even just say 0.3, right? The area of this little thing is 0.3. The area of this little thing is also 0.3. But the area of this tiny thing is like 1/100. That's like 0.01. So it really is like a whole order of magnitude kind of smaller than these two other pieces. And of course, if I now change that from 1/10 to 1/100, then it becomes even more dramatic, right? That's 1/100, that's 1/100. So now that becomes 0.03, 0.03, and that's also 0.03, but this over here is now like 0.0001. Okay, and so what are we kind of seeing? We're kind of seeing this theorem saying that, well, okay, I'll stop there. All right, two more. Take the derivative of x cubed. Well, of course, you can just report that this is 3x squared. But I claim, if you've never seen the following picture, then you really don't understand what the derivative of x cubed really means. And what does it mean? Well, it's right there in the name. The x cubed function is the function which tells you, has something to do with cubes. What is x cubed? It's the volume of a cube of side length x. Okay, so here we go. Bad art skills coming. But I did practice this, but it was a couple days ago. Let's see. sha, sha, sha. That's not terrible. So here's my my cube, although I'm too lazy or dumb to do like perspective and dashed lines and stuff like that. Okay, that's pretty good. So that's x, and that's x. So this is a cube with volume x cubed. Okay, great. What am I going to do now? I'm going to measure the rate at which the volume of this cube is changing. That's really what's going on. In other words, I'm letting this cube become infinitely tiny bit bigger, and by that I mean I'm letting x become an infinite tiny bit bigger, and I'm asking the question, when I'm taking the derivative of x cubed, I'm asking the question, what effect does an infinitely small change in x have on the volume of the cube? Okay, well now I just need to let this thing get infinitely bigger. And okay, I'm almost tempted to just like look at the picture on my iPhone of this, because I did such a good job. Now I'm sort of panicked I'm going to do worse or something. Okay, yeah, so I'm going to let this grow, okay, x is going to grow. How is it going to grow? It's going to get, just like here we let the side get bigger. It's only getting bigger in like one direction, right? So here we're going to let this get bigger up, out, towards us, and to the right. Yeah, I think I can handle this. So we're going to get a little tiny jump, 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 and now, okay. So, ooh, that's like a little bit too big. 1 second. Guess that's okay. Okay, I think that's pretty clear. What just happened? The cube got a tiny bit bigger. How much bigger? Well, it's just delta x bigger. So that is delta x. And then it also gets bigger in the out direction. So we're going to go out, 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 and out. Yeah, this is looking good. Shomp, shomp, and shomp. And okay, so this little increase was delta x, but of course this is also delta x, like out. And then it's going to go delta x sideways. So bounce, 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 shomp, shomp, something like that. And that's, I think I forgot a line. No, I didn't. And this is also kind of delta x over here. Okay, so what just happened? My cube got bigger. Now, did I draw the entire cube? No. I'm now ignoring, based on my deep understanding of things, the little tiny, infinitely small pieces, which I claim are insignificant. And so there are, in the basic kind of decomposition of the cube that you often see, this is the decomposition of the cube. This is actually a way to prove to new people how to cube a binomial, or the demonstration of the binomial theorem. And okay, what do you get? If you think of the big, this medium-sized segment as being x, and this tiny one as being delta x, then what you get are, in fact, 8 pieces. You have the original cube, x cubed down here. Then you have sort of this one that's shaped kind of like a big phone book. This one up here that's shaped like a big phone book. And this one up front that's shaped like a big phone book. Then you have these 3 sort of sticks of butter over here. And then you have this tiny little cube up in the front here, which has sides delta x, delta x, delta x. But the idea is like an infinitesimal is so small that when you multiply 2 infinitesimals, it's like just completely insignificant. It's a whole order of magnitude less. In the same way that 0.0001 is insignificant as compared to 0.03, and the same way that delta x times delta x was insignificant as compared to x times delta x, which gets borne out in the form of limit proof. If you don't like this geometric stuff, you can always just fall back on the limits, but I'm trying to give you some deep understanding. Well, then I'm not even going to draw these 3 sticks of butter, because they have side lengths which this is delta x, but this is also delta x. Okay, so, well, never mind, I'm not going to defend my choices anymore, because I think this is actually beautiful. This theorem is now popping out at us. What just happened? Well, each of these, this is x, this is x, this is x, this is x, and this is x. And so what I in fact see sort of popping out of this cube are three faces, or they're just three prisms. And what's the volume of this prism? It's an x by delta x prism. So that's x times delta x, and this prism also has volume x times delta x, and this prism is also x times delta x. Okay, so for every infinitesimal small change in the side length of the cube, how does the volume of the cube respond? The volume of the cube responds by popping out three phone book shaped extra sort of layers, and each of those has area x squared times delta x. And so the derivative is asking what is the rate at which this function is changing sort of with respect to the change in the input. That's just what a derivative is, right? Give me some infinitesimal small change. How does the volume respond? And the answer is that the volume of this cube grows at the rate 3x squared. But you should now sort of feel, when you see this 3x squared, you should sort of feel that the x squared is the area. It's an x by infinitely thin extra layer popping out of the three faces of the cube. And that's because x is getting bigger, and so the cube is getting the cube is growing. Okay, whew, I think I've made my point. It's taking too long. This was all supposed to be warm up to doing the geometric proof of the derivative of sine. And the idea, what I hopefully convinced you, is that there's like some whole other like underground calculus or something that's not in any of the textbooks, which in some ways is like the real calculus, which is describing the sort of actual kind of behaviors of these sort of geometric objects, you know, upon tiny increases in the input to the functions. And so it would be kind of like an intellectual crime or something to teach the derivative of sine without actually explaining what's really going on. What's really going on? I'm going to draw a picture. Before I draw a picture, I need to do a warm-up. And the warm-up is a proof that you should have seen when you were in Pre-Calc B, but I bet you didn't, because I know you're a Pre-Calc B teacher, and I know he doesn't do this. That's a decent quarter circle. It could be better, it could be worse. Okay, I would like to prove to you the formula for the sine and cosine of a sum. And I want to prove it geometrically, because only geometry is real, and calculus is just geometry of the infinite. Okay, how are we going to do this? Well, what is sine? It's the y-coordinate. So we begin. I'm going to draw an angle, alpha, or I guess just A. And I'm also going to draw an angle B. And, okay, so this is A, this is B, and therefore this whole thing is A plus B. Shot. And this is a unit circle, so A plus B. Okay, and now, what do I have up here? I have this point, and well, ultimately, what I need to know now is the height here. The height is going to give me the sine of A plus B, and this is going to give me the cosine of A plus B. Okay, and this is a unit circle, so this is all like 1 and stuff. Okay, so let's begin. What can I do? Well, it's basically like one smart thing that you need to do. So let me make sure that I do it. Yeah. Okay, and that is drop a perpendicular down from here to here. Why do I want to do that? I kind of want to do that because I have this. So this is a radius of the circle, right? So this is 1. And in some ways, like, this is the segment which is kind of not, this angle B is the one that's not, like, in standard position. So I need to sort of reason now about this b. So I'm going to kind of erase that a little bit. And I'm going to say, okay, now we're done. That was the sort of the only smart thing you had to do. Because now, well, if this is 1, then if I take the sine of b is opposite over hypotenuse. So it's opposite over hypotenuse. Therefore, this thing over here, this purple thing, has length sine b. And this thing has length cosine b. Okay, well now, what's the goal? The goal is to find the total height. And so I now decompose that height in 2 ways. From this point, I drop a perpendicular down. And from this point, I drop a perpendicular like up. Okay, and now I have to do a tiny bit of like thinking here. I might need to stop this video. Yikes. Yeah. So okay, if this is a right angle, if this is cosine b, then this triangle here has a hypotenuse of cosine b. But the sine is a. So what is the sine of a? It's just like, that over cosine b. In other words, this is cosine b times sine a. Because it's just the opposite, it's the opposite, it's the leg which is opposite an angle of a in a right triangle whose hypotenuse is cosine b. Or you could just say, take the sine of a, what do you get? You get opposite over hypotenuse, and so that must be cosine b sine a. Okay, and then similarly, this whole thing is cosine b cosine a. It's the adjacent leg to an angle A in a right triangle whose hypotenuse is cosine B. And, okay, well then what's or you can think of it as the cosine of A is adjacent over hypotenuse. Okay, and now I have to work out the dimensions of this little right triangle. Well, here I have to use like a tiny bit of geometry. This is A, so that makes this angle right here the complement of A, right? These two are complementary angles. They add up to 90, or since we're in radians, these add up to pi over 2. But now that's a right angle, so these two are also complementary angles. These two add up to pi over 2. In other words, this is supposed to be easy, but my experience is that some students find this hard. This is A. This angle is A. Maybe I should use some, instead of these arrows, maybe I should call this like a 1 thing, or let me call this like 2. And this 1, well then this is also like a 2. These two are equal because they're each complementary to this angle. Okay, and that was the only thing I needed, because now I have a little right triangle whose hypotenuse is sine b. Therefore, this angle here is sine b cosine a, this side, and this one up here is sine b sine a. And now we are done. What is the sine of a plus b? Answer, it is the height. This is the angle a plus b, so its height on the unit circle is this dotted black line, which is just, read it right off, it's sine a cosine b plus cosine a sine b. And what is the cosine of a plus b? It's this right here. It's this thick black thing that I just drew in. And what is that? Well, that is cosine b cosine a, so cosine b, minus this little bit up here, sine a sine b. This is, in my opinion, the absolute best, most perfect, really no competition, a way of deriving the sine of a sum and cosine of a sum formulas. It's all there in one picture. It flows perfectly from the definition of sine and cosine on the unit circle. It involves sort of a little bit of geometry, and it's really perfect. All right, why am I bringing this up? Because what I want to do right now is assume that you've done something like this before as kind of background knowledge, so let's go. Without further ado, and then we'll stop this video, I guess. I'm going to prove to you the formula for the derivative of sine in a way that actually makes sense and is meaningful. Okay, so what's the derivative of the sine function? All right, here we go. Proof via picture. I got to do this in like 2 minutes. That's a kind of a quarter circle. Could be worse. Let this be a unit circle with radius 1. Now, what am I going to do? I'm going to take a certain, a certain angle, x. And then, what I'm going to do is I'm going to let that angle get a tiny, oh, and by the way, if this is x, then really what's going on is that the length of this arc is x. Chop. Okay, and now I'm going to let this angle get a tiny bit bigger. And, okay, this then is delta x. It's this tiny, kind of infinitesimal small increase. And, okay, so that makes this little bit here, maybe I'll do it in red. This is delta x. Hopefully this is going to look good. Okay, sure. Maybe I'll draw it on the inside. This is delta x. Okay, great. Now what? Well, what is sine? Sine is just the height. So that is sine. And now, what do I have to do? I have to find the sine of the new thing, right? So what is the derivative? It's just kind of like, it's the change in the sine function with respect to a change in x. In other words, it's sine of x plus delta x, sine of x plus delta x minus sine x all over delta x. This just appears that I'm writing out the normal definition of the derivative, and I am, but instead of using limits, I'm just thinking of delta x as being infinitely small. Okay, well, great. What's left to do? I have this dotted line here, and this dotted line, this dotted blue line, is sine of x plus delta x. So let's just find out what that blue line is and subtract. Well, in other words, what I really need to know is this little bit here. So now I'm going to draw in a triangle, but what is it really? I'll just be vague about that because that's kind of more in the spirit of the exercise, right? But I'm just going to sort of go up almost in the exact same way that I did before, and now all the sort of same things hold. Look. This is just a right angle. Maybe that's the most controversial part. Is that really a right angle? Well, it's a right angle if that red thing were a tangent line. That red thing is not really a tangent line. It's actually just part of the circle. But if delta x is infinitely small, then it's basically just a tangent. And if it's basically just a tangent, then it's perpendicular to the radius. And so you might as well just think of this thing as a triangle, even though it's not really a triangle. It's really two segments and this archy thing, but the arc is basically just the hypotenuse of that triangle when the arc is infinitely small. Okay, finishing this up by the exact same logic that we just used so we can go faster. If this is x, this is the complement of x, so this is back to being x again. So this little angle is also x. And now, what do I have? I have a little right triangle whose hypotenuse is delta x. And the, let's see, the other piece I needed was this one. So what is this piece? This piece is delta x times x. Times cosine x is what I meant to say. Times cosine x. Because it's just the adjacent side of a right triangle with angle x. It's the side adjacent to an angle x in a right triangle whose hypotenuse is delta x. Another way of thinking about it is you just take the cosine of that angle. What do you get? You get, this over the hypotenuse. And so, therefore, this must be that. All right, and that's it. We finish. What is what is this numerator? Well, it's the amount by which the sine function changed over that infinitely small period of time. And so if this was sine x, and I let my angle get an infinitely little bit bigger, then what happens to the sine? It gets a tiny bit taller. How much taller does it get? This much taller. This delta x times cosine x is the amount by which the sine function grows when that arc gets a tiny bit bigger. And therefore, this numerator is delta x times cosine x, and that completes the proof. The real reason why the derivative of sine is cosine is because sine, upon the angle getting tiny bit bigger, the sine pops out a tiny little extra amount of height. And that extra amount of height is, by sort of triangle similarity, these two triangles are similar, is really just the cosine of the angle at which this is all happening. Okay, hopefully you enjoyed that. Be back for more later at WEC. Okay, hello, back for a little bit more. This is the next day. Now that we've seen some basic derivative formulas, sine, cosine, we're going to prove for homework, and polynomials, let's talk about something else, which is also in this same section from the textbook, and that is this concept of a second derivative. So, okay, if I give you a function and I tell you that this is a position versus time curve, then, as we've been talking about over and over again since the beginning of this differentiation unit, that if I pick a particular point on this curve, some kind of time like a or whatever, and all right, suppose let's just call this function, just call this function f, and yeah. So here I have this point, a comma f of a, and as we've been discussing, that if we take the slope of the tangent line to this curve, then what we get is a velocity. And I've probably already kind of mentioned this, and this might be the kind of thing that's very obvious to some of you, but okay, and where did this come from? We got this second point, x comma f of x, and we made the secant line through those 2 points, sure. And then we move those 2 points infinitely close together, and okay, and for all the reasons that we've already talked about a million times, the slope of the blue secant line is the average velocity over the interval ax, and if I move this point x infinitely close to a, then I get the instantaneous velocity. So if this is a position versus time curve, then the derivative of f at a is the velocity at time x equals a. Okay, and great. So that kind of thing was sort of, I don't want to say well known, but this was done by people prior to Newton and Leibniz. I'm pretty sure I have said this already, so I'll just say it quickly. Finding the individual slopes of tangent lines, finding slope, given a particular curve and a particular point on that curve, being able to calculate the slope of the tangent line to the curve is something that people knew how to do 30 or 40 years before Newton and Leibniz. But the thing that Isaac Newton in particular did, and Leibniz did this as well, and it's this sort of move which brings us kind of boldly into the world of real calculus now, away from geometry and towards some sort of new thing, is this process of creating the derivative function. And if you think about it, this process of finding the derivative of f at a is already an infinite process. It's an infinite process in the sense that I'm considering when I let this second point x be variable, I'm considering actually simultaneously an infinite number of x values. And therefore, I'm letting the second point here of this secant line represent simultaneously sort of an infinite number of different points. Another way of putting it is I'm considering an infinite number of secant lines. And I'm making some statement that says, all of those secant lines have this kind of property or something that, when the number x is very, very close to a, but I'm still considering sort of an infinite number of different x values, then the slope of the secant line is sort of very, very, the slopes of the secant lines are very, very close together. Literally, they have a limit. Okay, so this is just what we mean when we say a function has a limit. So considering this whole entire thing as the function, which is really what I'm doing when I'm defining the derivative, I'm really sort of considering an infinite number of secant lines. Okay, but that is just giving me one derivative, f prime of a, which is one number. I am now going to a whole nother level of abstraction when I define the derivative function. And so the derivative function now is a whole function which is giving back for any input the derivative. And so this process, this infinite process that I'm performing at this particular point, x equals a, considering an infinite number of sort of converging secant lines, by taking the derivative, I actually perform that infinite process an infinite number of times simultaneously on every single point of that curve. So I don't know. I think that's kind of crazy. Just to take kind of an example for a second. If you give me some function, say x cubed, and you ask me for the derivative at 2, well, I am then considering kind of an infinite number of secant lines, all of which have this slope, and I'm going to look at all of them, and I'm going to determine that all of the secant lines, which are very, very close to 2, let's see, can I do this in my head? Sure I can. All are basically 12. Okay, but then when I take the function x cubed and I take the derivative of this function, I am really doing this process an infinite number of times. And then what we get is this new thing, 3x squared. So it's the move away from geometry and towards kind of algebraic manipulation, which gave Newton the flexibility to sort of construct this new thing called the derivative function. And it's thinking of the derivatives like as a function, which is kind of like his big advance. And I'll just say before I move on that you can even take this up to even a higher level of abstraction, because you can think about what we were doing when we differentiated x to the n, and we concluded that this was nx to the n minus 1. This is even another level of abstraction, because now I'm not only asking you to perform this infinite process to find the slope of the tangent line at a point, I'm not only asking you to perform this infinite process an infinite number of times at every single point in the domain of that function, but I'm asking you to do this simultaneously for an entire infinite family of functions, all of which are in like a certain kind of form. So okay, this is I think there's actually kind of a lot going on. Alright, so why is it so exciting that Newton can perform differentiation on the entire function at once? Well, because of now the flexibility it gives us to define concepts in physics. And basically, what Newton does is start with a position function, and it's convenient to do what the physicists do, and to let our independent variable be t, just because we think of t as time. And for whatever reason, we use the letter s for position. P is sort of already taken or something. So let this be let s of t be a position function, and what Newton does, and which is now absolutely standard, is to simply define velocity as the derivative of position. And so I hereby say, take the derivative of the position function, and I'm going to call that velocity. In other words, what you will find if you take, the next physics course that you take in your life will be a calculus-based physics course. And in a calculus-based physics course, they will simply give as their definition of velocity. The very physical concepts themselves will be defined in terms of calculus. They will tell you that the definition of velocity is it's the derivative of the position.
And so by taking Newton's ability to perform differentiation an infinite number of times simultaneously on every single point in the domain of a function to produce a new function, we may now sort of do calculus things to an entire function. And I immediately sort of create, by this process, a new function, which is velocity. And why is it so nice to have created an entire new velocity function? Because there's nothing stopping me from performing this operation again. So what happens if I take the derivative again? Well, there's a name for this. We call this the second derivative. So when you see a little don't up here, so with two little primes, then people call this s prime, people call this s double prime, and the second derivative of position, which is just the derivative of velocity, is the instantaneous rate at which the velocity is changing, and that is just acceleration. So that's just kind of what acceleration is, right? Acceleration is the rate at which the velocity is changing. So just like velocity is the rate at which the position function is changing. And once again, our definition of acceleration is just the derivative. So you will just define, in the next physics course you take, you will define the acceleration function to just be the second derivative of position. Okay, and there's nothing to stop us now. We can just keep on going. And there are all kinds of kind of goofy names for this, like the jerk. So the jerk is like the rate at which something is accelerating. The idea being like, I don't know, if you're in a car or something and someone hits the gas to accelerate the car, well, if you do that smoothly, you know, you'll keep speeding up and speeding up and speeding up. But if you like jam your foot on the brake, then you'll like jerk backwards and, you know, spill your drink all over your lap or something. So the jerk is the rate at which something is accelerating. And what is the jerk? It's defined to be the derivative of the acceleration. In other words, it's the second derivative of the velocity. In other words, it's the third derivative of position. And okay, that's about the only one you're ever going to see in your like real life or something. But you can keep on going, right? There's like snap. What's snap? Well, it's like the rate at which you are jerking or something like that. You know, you just snap your neck in half or something. So this is, personally, I don't see ever using this in my life. But what's snap? Well, it's like the derivative of the jerk. And which is, therefore, the second derivative of the acceleration, which is the third derivative of the velocity, which is, okay, and anything beyond 3, people start using this other notation, which I'm teaching you now, which is instead of putting 4 little thingies up there, people might even start at 3. You just put it in parentheses. So if you ever see this symbol, you will know that that means the 4th derivative of the position function. And that's just the definition of the snap. Okay, good. One more little thing on this topic. And actually, we're going to sort of return to this later on, like a month or something. But for now, looking back on this kind of amazing fact about sine for a second, if I give you the sine function, well, let's just differentiate it. What do we get? Well, the derivative of sine is cosine. That was exciting. What's the second derivative of sine? Is just the derivative of cosine. We saw that the derivative of cosine is negative sine. Well, what's the third derivative of sine? Well, the derivative of sine is cosine, so this is negative cosine. And the 4th derivative of sine is the derivative of negative cosine. The derivative of negative cosine is negative sine, so it's back to being sine again. So there's some kind of like cyclic thing going on here. And this is kind of amazing. You could sort of dwell on this for a long time. At this moment, though, I would like to focus on this relationship, which is that sine is actually its own, is a function whose own second derivative is the opposite of itself. Is there some kind of meaning? Can we extract some kind of meaning out of this? Yeah, I sort of think so, right? What is sine? It's kind of like the function, and cosine also has this property. And so does any sum of sines and cosines have this property. the second derivative is always the opposite of itself. Okay, well, how should we think about sort of second derivatives? What do they sort of mean to us? Well, one thing they mean is that they are the acceleration. And so if you think about sine, sine is a function which describes an object such that the position of that object is the opposite of the acceleration of that object. Do you know such a thing? I say yes, you do. Okay, I'm a little bit out of my comfort zone here because I'm going to try to do some physics, but I'm probably not going to mess it up. So you take an object, take a sort of object on a spring, or a mass, hope I get this right, a mass on a spring. And okay, so let's draw that spring and jump, 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 jump. And let this be the equilibrium position. So this is the mass on the spring. In other words, you know, if you let it go, well, this is I think everyone knows what equilibrium position means. If you sort of do nothing, this is where the mass will just kind of settle down. Okay, and ignore gravity and stuff like that. So, all right, what we have here now is this situation where we're going to call this 0, and I'm going to measure position in terms of being, you know, bigger than, so to the right of 0, to the left of 0. And so if you have, if the mass on the spring has positive position, then it means that the mass has been stretched out, so the spring is being stretched. And if the object has negative position, then the spring is being compressed. Okay, I probably should have practiced this picture, but I think it's going okay. Maybe I should draw it sort of 2 more times. So let's see, something like this now. 1, 2, 3, 4, 5, 4, 5, and then here's this, and then this is still the equal 0, and then there's kind of like the stretched version, right? So 1, 2, 3, 4, 5. Yeah, this is looking great. Okay, and so what we have here is sort of position 0. Here we have a negative position. And here we have a kind of a positive position. So, okay, great. Well, there's this thing called Hooke's law, and the thing called Hooke's law says that something like the force on the object is proportional to the displaced, to the opposite of this. It's some kind of crap like this. It's like F equals negative kx. I mean, I think you just learned this even in freshman physics. I don't know how they teach this, whether they just simply give it to you as an empirical fact that's been observed, or whether there's some sort of theoretical derivation. I suspect not with the theoretical derivation. But okay, accept this for a minute. What is it telling you? And what does the negative mean? Well, force is just mass times acceleration. So if you do mass times acceleration, the mass of the object is not changing, equals negative kx. Then let's just ignore the mass for the moment, and also let's ignore the k, because it's just some kind of constant to make the units match up. And so really what we have here is that the acceleration is proportional to, I think people use this symbol, the opposite of x, where x is kind of the position. And maybe I'll even just write, you know, position here. So position. What this really means is that when the position is negative here, not sure how exactly to label this, I'll just say S is negative, that's a negative position, then what happens? Well, the object being compressed means that some kind of force now is being generated, and the force is going to push the thing that way. And so what we have now is some kind of force in this direction, and okay. And here we have a positive. We have a positive position, and then that generates a force backwards. And so, what can I say about an object which is bouncing around on a spring? If this is the only force acting on it, well, its force is always proportional to the opposite of its position. But ignoring the mass for a moment, what this is, just sort of let the mass be kind of absorbed into the constant. What this is really saying is that, ignoring units and stuff, that we have an object whose acceleration, so let f, how do I want to put this? Yeah, let let f be the position function. Let's do it like this. Let f be the position function. And if f is the position function, then what kind of position function describes this reality? Answer, a position function in which the acceleration, otherwise known as the second derivative of this function, is equal to the opposite of the position itself. And so here we have now, we sort of seeing once again the power of calculus to describe or to kind of solve a physics problem. Here we have a physics problem in which some object is moving such that at any given moment the force on that object is proportional to the position of that object relative to some equilibrium position. And from this situation I extract that whatever the position function is describing this mass, this mass is going to move kind of back and forth and back and forth and back and forth. If you compress it and then let go, it's going to go out, but then the force is going to pull it back again, but then the force is going to push it out, and it's going to sort of go back and back and back and forth and back and forth. But how does it go back and forth? Answer, it goes back and forth in such a way that the acceleration on that object in any given moment is some constant times the opposite of the position at that moment. And we have seen up above here that, that sine is precisely one of those functions. And so, being very kind of casual now, I'll just say that the solution to this problem is that f is sine. Or it could be cosine, and there's going to be some kind of constant in there, and whatever else. But basically, I have just proven to you, it's a very casual proof, that if you accept Hooke's law, then, in fact, by setting up, this is what's called the differential equation. A differential equation is an equation in terms of a function and one of its derivatives. And just by experience, we've seen that one solution to this differential equation is the sine function. Here I've just now proved to you that an object bouncing on a spring is going to move sinusoidally. Okay, good. Be back for some new stuff in a minute. Okay, we're back. It's time to look at some of the other basic functions of precalculus. What are all the functions of precalculus that we know? Polynomials, of course, algebraic functions, square roots, cube roots. Okay, we know how to do those now. More complicated things like rational functions, we don't know how to do that yet. We saw the derivative of sine and cosine, so you might be thinking, you know, what about everything else? What about the derivative of tan and secant and, you know, e to the x and stuff like that? Okay, I got you. Let's go. What is the derivative of e to the x? This is kind of an amazing thing. You could spend anywhere from 1 minute to 1 hour, you know, talking about this. Of course, I want you to understand, you know, potentially everything. So the meaning of this, why I should care about this, where it came from, the history, the whole point of it. What is even E anyway? The proof, of course. Maybe the geometric interpretation, something like that. Okay, so let's go. First of all, before I can even talk about E, to the E to the x function, I have to kind of know about this function a little bit or care about it or something. Let's just recap very quickly everything you already know about this function. Well, you know, not much. Not much. In fact, yeah, this is not the kind of thing you learned in Algebra 1. This is the kind of thing you learned in pre-calc. It's because E is kind of a tricky thing, and you might even be right now thinking, why should I care about E so much? Does it have something to do with interest or something? So let's just start with the fact that, you know, maybe we don't like E or something. Maybe we like 2 to the x. Maybe that's just like a much nicer function. I've had students tell me in years past, even when they got to this moment in calculus, they were like, yeah, this is a little bit, this function, yeah, I don't really like this one. Why not? It's kind of like annoying, all the values are irrational. What is E anyway? E squared, I don't even know what that is. It's like 7 something. It doesn't fit on the little dots. Whereas, consider nice, happy, comfortable 2 to the x. Anyone can graph 2 to the x. Even a child, like an Algebra 1 child, can just pick some simple, nice numbers and plug them in to the x function and can get a good idea of what's going on. All you have to do is just understand what exponents are. Maybe you have to be a little bit comfortable with negative exponents, and but let's just say that we are comfortable with them. And boom, what do you know? Here is a happy little function that I have just graphed, and boom, boom, so something like this, and then, okay. So, isn't that so wonderful? Why do I need e to the x in my life, you might be thinking? Well, I would just like to say that though we have produced a simple x comma y chart and plotted these points, I made quite a bold assumption when I just sort of connected all these points with some kind of curve. In fact, I've just decided that this function is continuous. And okay, in pre-calc B, hopefully you have this conversation that there's actually kind of a lot of confusing sort of stuff going on here. And even something as simple as the 2 to the x function, I'm of the opinion that these should just not be presented in Algebra 1 because they're too hard. But okay, maybe, you know, we live in a world where, you know, you can't wait or something. Exponential growth is like somehow important. And maybe, you know, doubling as a process is maybe very simple to understand. If something is growing exponentially, you know, that's something that I would like to know and understand. But okay, you know, whereas this is perfectly clear for positive integers and also clear for negative integers, if you ask me what like 2 to the 2/3 is, you know, that suddenly becomes less clear. Okay, I do know what 2 to the 2/3 is. You know, it's the cube root of 2 squared, or alternatively, it's 2 squared, the cube root of that. So this is just the cube root of 4. So I have a clear interpretation of what it means to raise 2 to some sort of rational power. But like, what is like 2 to the root 2, for example? I bet that you either have no idea what this is, or this never came up in pre-calc B, or you just never thought about it, or possibly just don't care. But at this moment in your life, you really just have no interpretation at all of what 2 to the root 2 means. And so actually a lot of, we're hiding quite a lot of stuff is being sort of hidden here by our decision to sort of connect 2 to the x with a kind of with a smooth curve. In particular, I think I only really understand the 2 to the x function when the input is rational. When the input is irrational, I think I don't really get it. And it's not just a matter of me not being able to compute it. Like, I literally don't even know what 2 to the root 2 even means. So root 2 is 1.41 something something, etc., etc. I should probably know more of those. 412? I actually don't remember. 1 point maybe 4 to 1 2. I'm not even sure if that's right. Okay, and so, you know, this kind of goes on and on. So what is root 2 exactly? Well, it's 1.412. So okay, so it's approximately equal to 1412 over like 100. No, over 1,000, I mean. And so one interpretation of 2 to the root 2 is that it's approximately 2 to the 1412 over 1,000. And that now gives me a understanding of it. So in other words, just sort of treat irrational numbers like approximately equal to some rational number. Okay, putting that all off to the side, what's up with this e to the x function? What is it? What does it mean? Why should I care about it? Well, I can't say for sure why you should care about it, but when it came up is in compound interest problems. Okay, so without, let's see, maybe I'll erase this because that was a little bit of a possibly unnecessary diversion, but let's just at least mention that there's this compound interest formula, and we developed it carefully, you know, based on some basic kind of principles. It was something like this. Was the formula, and in fact what happens is if you compound n times per year, then every 1/n of a year we sort of stop the clock and we look at how much more money you've earned, and what happens is it's a geometric sequence because we are multiplying by 1 plus r over n to the n, sort of every 1/n of a year. Okay, anyway, we end up with this formula, and then we ask, what happens if you give me $1 for 1 year and at 1% interest? And the answer is that A is going to be, 1 times 1 plus r is now 1 over n to the n times 1. And so it seems that the amount of money you end up with after n years is determined by, the amount of money you end up with after 1 year, after investing $1 at 1% interest, is 1 plus 1 over n to the n. And if n is, say, 1, then you get $2. If n is 2, you get something like $2.25, etc., etc. And then we, in pre-calculus, pose this question, well, how does the amount of money I eventually end up with depend on the number of times per year I compound? And if you take the limit as n approaches infinity of this entire thing, then it's not actually obvious at all that this does have a limit, but it does have a limit. And the answer is you get this number that's like 2.71 or something like that. Okay, so this is E. E is this number which keeps coming up again and again, and it's basically the solution to the question, what happens when you invest $1 for 1 year at 100% interest. Sorry about that. 100% interest. Okay, right, and then via a sequence of clever substitutions, which actually will be a lot easier for you now that we've been doing limits for the past couple of weeks, you then in fact prove that actually E is sort of the base of this exponential function, which tells you for a given amount of time how much money you're going to have in the bank if you are compounding continuously. So in other words, if you let the number of compoundings approach infinity, then you get this. Okay, and so exponential functions are sort of important, or specifically, exponential functions are important, but specifically the e to the x function is supposedly, to a pre-calculus student, important because anytime you are doing compound interest calculations in which you are compounding continuously, then it describes, the rate of growth of that function, or of that money. Okay, great. Yeah. So there's sort of these two definitions of E floating around. Maybe I'll mention them right now. Here's one. E is the limit as n goes to infinity of 1 plus 1 over n to the n. But there is another equally valid, perhaps more convenient definition of E, which is just what you get when you perform like a limit switchy on this. So, let's do a little thing where we say let A be 1 over n, and now observe that as n approaches infinity, A approaches 0 plus. So with this fact, we may therefore define E slightly differently in terms of A instead. So it's now the limit as A goes to 0 of 1 plus A to the 1 over A. I guess if we're being careful, I should write 0 plus. But it actually works from both directions, though that's not obvious. Okay, good. So I got two definitions of E floating around. These are the definitions that came up in pre-calculus, and you maybe sort of have a feeling that therefore this function's important. But the real importance of this function comes now. Let me erase this, and let's just find out what the derivative of this function is. Okay, well, well, how should we do this? Should we draw a picture or something like that? Well, it's even just annoying to draw a picture of e to the x, actually, because, like my students were telling me 5 years ago, e doesn't fit nicely on the numbers or something. But okay, too bad. If I plug in 0 to this function, I get back 1. If I plug in 1, I get back e, so that's going to be up here at e. If I plug in 2, I get back, e squared, and something like this. 1 over e, I don't know, it's like a third or whatever, so blah, blah, blah. Okay, so I have some e squared is like 7, so I have some exponential function. How fast is an exponential function increasing? Pretty fast. In fact, an exponential function. Okay, I won't ruin it. So what should we do? I can't think of any sort of deep thing to do here, so I'm just gonna start. And by start, I mean use the definition. So getting to it finally, the derivative of e to the x is the limit as h approaches 0 of f of x plus h minus f of x over h. Is the general formula for the derivative of any function. So for the derivative of this function, it's going to be the limit as h goes to 0 of e to the x plus h minus e to the x over h. And here I can think of basically only one good thing to do. When I was taking the derivative of power functions and I had x plus h to the n, there was only one good thing to do, which was to just expand that out using the binomial theorem. When I was taking the derivative of sine and I was trying to find out that, there was only one good thing to do with this sine of x plus h, and that is to expand it out using the formula for sine of a sum. Well, here I have e to the x plus h. This is the easiest one yet. How do I expand e to the x plus e to the x plus h? Well, I just use basic exponent rules to write this as the limit as h goes to 0 of e to the x times e to the h. And there it is. Alright, and now something kind of wonderful but perhaps confusing has happened, which is I now have an e to the x in both terms of this numerator. Perhaps I'll just write it out one more time, over squeezing it in over here. So the limit is h approaches 0 of, so I get this e to the x times e to the h minus 1 over h. And now, this is a little bit of a follow-up to the previous conversation we had from the other video, but this is the limit as h goes to 0. So e to the x is like a constant with respect to this limit. Therefore, I can just pull it out entirely. And what I get is, therefore, e to the x times the limit as h goes to 0 of e to the h minus 1 over h. Okay, and so I set out to find the derivative of the e to the x function, which means what is the rate at which this function is increasing. And if you didn't know anything about this whatsoever, anything is possible, right? It's turned out, after just 2 or 3 short lines that weren't even very difficult, that the answer is e to the x times some limit. And what is this limit? Well, I don't know what this limit is, but this limit is going to be some kind of number. And this limit, so I'll just write like question mark or something, because I don't know what the answer to this limit is. But if I can simply calculate whatever, if I can just find out what this limit is, which is going to be, presuming this limit exists, this limit is going to be a number, so it does exist. Once I find it, then the shocking answer to this problem is I'm already shocked. I'm not done with the problem yet, but I'm shocked, because it turns out that the derivative of e to the x is e to the x times some constant. Okay, in other words, the rate at which this exponential function is growing is an exponential function times a constant. In other words, exponential functions grow exponentially. And this is something that you maybe kind of already know. Because, now this is maybe a little bit repetitive or something, because we just did this a couple days ago, but okay, too bad. So 2, 3, 4, 5. We've already been looking at these polynomial growth rates. I can do this in like a couple seconds. And what is there to say about the rate of growth of x squared? Well, it's going up by 3, up by 1, up by 3, up by 5, up by 7, up by 9, and by looking at the second, so-called second finite differences, the differences, I see that this is constant. And what was our conclusion there? Our conclusion was that quadratic functions grow at a linear rate. Okay, what about cubic functions? What's the rate of growth of a cubic function? Well, 8, 27, 64, 125. Well, we saw in class yesterday that that this is going up by 1, up by 7, up by 19, up by 37, up by 61. And what are those numbers? Well, I'm not sure yet, but that's up by 6, up by 12, up by 18, up by something 24. And these numbers are constants, so this is linear, this is quadratic. In other words, cubic functions grow at a quadratic rate. All right, let's just try this same thing. It's possible that Mr. Kirk did this exact lesson with you last year in Pre-Calc B, but maybe not. What can I say about exponential functions? Well, let's try to do the same thing. So this is like 3, 4, 5. What is the rate at which exponential functions are growing? Using 2 as a simple example. Well, this is 2 to the 0 is 1. 2 to the 1 is 2. This is 4, 8, 16, and 32. Okay, let's look at the finite differences. If you've never done this before, be prepared. How fast is this function increasing on this interval? Well, it's going up by 1, up by 2, up by 4, up by 8, and up by 16. What? Yeah, that's right. Exponential functions increase exponentially. The rate at which an exponential function grows is itself an exponential. This is unlike any other kind of function that we know of, like polynomials and stuff like that. These functions grow so fast that, okay, I'll stop there. All right, so, and maybe I'm even going to erase this middle because I do want to kind of finish this problem. What is this? What is this limit? How can we find this limit? And therefore sort of complete this problem? Well, I don't know. Okay, I don't really know what else I can possibly do here. And actually, anything I try to do, there's no sort of algebra tricks, there's no common denominator, there's no multiplying by the conjugate, there's none of that. And so I'm sort of forced to, and maybe this is obvious to you, that you're forced to actually use the definition of E somehow. And the definition of E is down here on the bottom of the board. So let's try to use the definition of E to do this limit. And okay, there are a lot of ways to do this. And what I'm going to do right now is something I've never done before. And maybe this is good, I don't know. But this is sort of due to a friend of mine, or maybe he got it from somewhere else. In order to solve this, let's use logarithms. So, okay, it's very not clear to me how to solve this problem. So let me, actually, hold on. Before I start trying to solve it, first let me understand it. And, okay, maybe you're already, just stare at this limit for a while. Stare at it, stare at it, stare at it. Look at the graph. E to the h minus 1 over h. If I try to plug in 0, of course I get 0 over 0. It's a 0 over 0 situation. The numerator is like the difference of two things. This is looking to me awfully like a derivative. And in fact, if you just throw in a little minus 0 down there, it's starting to look a lot like a derivative. Take some point over here, h comma e to the h, and of course this point here is 0, 1, and well, what do you know? This, in fact, is the slope of the secant line through those 2 points. And I just drew it right there. Hopefully that's kind of visible. Let me just make my graph a little bit, like that. Okay, so, what is this little bit here? this little bit is e to the h minus 1, and this little bit is just h. And so in fact, this quotient is the slope of the secant line through 0, 1, and a point which is a tiny bit more than 0. In other words, how should I be understanding this limit here in blue? It is itself a derivative at a point. It's the derivative of the e to the x function at x equals 0. So I still don't know the answer yet, but the thing I'm actually looking for, the thing that will solve this entire problem is, what is the slope of this line? What is the slope of the tangent line to the e to the x function at the point 0, 1? And it's going to turn out that the derivative of this function overall is just the function itself times whatever the derivative is at this particular moment. Okay, maybe I should just tell you the answer right now. The answer is, quite shockingly, that this line has slope 1. The derivative of e to the x is e to the x. Alright, that is, I think, really, really incredible. Once I finish showing you that this limit in blue is 1, what that shows is that the constant in this case is just 1. And e to the x is this sort of magically amazing function. It's a function whose rate of growth is itself. What that means is that at any particular moment, we can look at a point on the graph of e to the x, and we can draw the sort of tangent line at this point, and the answer is, this is the point e comma e squared. What is the slope of this tangent line? Answer, it is e squared. This is a function which at every single moment is increasing at an instantaneous rate equal to its own value. Okay, maybe now I gave away the excitement, but okay, that I think is what's kind of incredible. What I erased already is an intuitive feeling that exponential functions increase exponentially. What this shows about the e to the x function in particular is that it's the specific function which grows specifically at a rate equal exactly to its own self. Okay, how do we show that this is 1? There are a lot of ways. Some of them are more sort of hand-wavy than others. I'm going to do this new thing. So I'm going to introduce logarithms. And specifically the natural log. I'll assume that everyone knows the natural log. What is the natural log function? It's the inverse of the exponential function. So the natural log of e to the something is e to the ln of that something, and that's just x. This is just what it means to be an inverse. The composition of the e to the x function and the ln function are the identity function. Okay, and so I'm going to introduce this new thing k. I'm going to say, okay, let k be the numerator here. So let k be e to the h minus 1. Okay, if k is e to the h minus 1, then, alright, note that as h goes to 0, what can I say about k? Well, e to the 0 is 1, so k also goes to 0. So as I have been doing, I shall now, just like we always do, I will now take this limit in blue, and I will rewrite it, trying to judge my space. I will rewrite it in terms of a new variable. So what do I get? I'll start like over here, I guess. So I take the limit as h goes to 0 of e to the h minus 1 over h, and I rewrite it in terms of k's. So it's the limit as k goes to 0 of, in the numerator now I have a k, and in the denominator I have, well, what do I have? What is h? If k is e to the h minus 1, then that means that k plus 1 is e to the h, which means, by taking the natural log of both sides, that the natural log of k plus 1 is h. So this denominator now becomes ln k plus 1. Cha. Okay, Has that made my life any easier? I don't think so. If I try to plug in 0 for k, I get 0 over 0 situation. There's no obvious advantage of this. But I know a lot of things about logarithms. And, okay, I want this k to be a coefficient of this natural log. So I'm going to rewrite this as 1 over k times ln k plus 1. So that's just some fraction kind of manipulation. And now there's sort of one more kind of brilliant thing to do here, which is to use another old fact about logarithms that you already know, that the natural log of, let's see, how do people write this? A to the n is n times the natural log of a. Okay, I'm not going to go into the explanation of why that's true right now. I'll just suppose that you know that, basic property of logarithms. Well, then you can also just pop that thing back up. So this becomes the limit as k goes to 0 of 1 over, and then that's ln of k plus 1 to the 1 over k. Chop, chop, chop. Okay, and the understanding is all of that is inside the natural logarithm. Okay, what is this? Well, this is now starting to look a lot like this. In fact, it looks exactly like that if I just do this. Chop, chop, chop. What is 1 plus k to the 1 over k as k goes to 0? Answer, it's e. I warned you that we would use the definition of e eventually. And this is the particular variant of the definition of e that we are about to use. Okay, and depending on how much more you kind of want to write here, one thing you could do is you could use some basic limit laws to say that this really becomes, I don't know how much more, once again, I don't know how much more you want to write, but this is really 1 over the limit as k goes to 0 of the natural log of 1 plus k to the 1 over k. And you can even just say that this is 1 over the natural log of whatever the limit as k goes to 0 of 1 plus k to the 1 over k is. And as we reviewed, that thing inside the brackets, by definition, is e. And so this becomes 1 over ln of e, and this is therefore 1. Okay, we did it. This is the part that I think is quite tricky. Is the determination of determination of this limit. That green marker is basically invisible, but whatever. So that I think is the hard part. Is calculating this limit. But don't let that sort of take away from the big picture here, which is that we basically just followed the definition of the derivative. We got stuck here, and then we did some kind of fancy moves to show that limit is 1. So okay, good. I want to erase something, but I don't know what to erase. Maybe I'll just erase everything. Yeah, be back in a second. Okay, that worked for e to the x. What if I just try the same trick over here at 2 to the x? It's very frustrating to not have a larger board because what I want to show are the exact parallels between trying to find the derivative of 2 to the x and the derivative of e to the x. But okay, we just begin immediately. Let's just do it. Without even thinking, this is the limit as h approaches 0 of f of x plus h minus f of x all over h. So we just stick the function in. It becomes the limit as h goes to 0 of 2 to the x plus h minus 2 to the x. So far, so good. Okay, what am I going to do now? Well, once again, I can apply that same exponent rule, and this becomes, 2 to the x, 2 to the h, minus 2 to the x over h. And then, once again, I can factor 2 to the x out. And if I do that, then I can then just take it right out of the limit, right? So this becomes 2 to the x times the limit as h goes to 0 of 2 to the h minus 1 over h. And okay, usually I stop and do this kind of halfway through the derivation of the derivative of e to the x to show kind of like the analogy between the two processes. This is exactly what we did to with e to the x, and we get to almost the exact same point. What do we observe? We observe that there's this limit here, which I don't know, but this is going to be some kind of limit, assuming that this limit exists. The answer to this limit is going to be a number, and so there's sort of no difference between e to the x, 2 to the x, 3 to the x. It doesn't matter what the base of your exponential function is. We've arrived at the same sort of shocking conclusion, which is that the derivative of the 2 to the x function is the 2 to the x function itself times some constant. So whatever this limit is, it's going to be a number, it's going to be a constant, and it's going to show that not just e to the x, but every exponential function increases at a rate which is exactly proportional to itself. And I can once again make some sense of this limit. What is it? Well, just like over here, I drew a picture of e to the x to get us kind of motivated or whatever. So this is like 1, 2, 3, and now maybe I don't even want to go all the way up to 3. So 2 to the 1 is 2, and then here we are at 1, and negative 1, a half or whatever. So okay, so here's my 2 to the x function, and alright, I've erased the e to the x function, so it's hard to compare them, but of course e is more than 2, e is 2.7. So this 2 to the x function is going to grow a little bit, well, it's going to be a little bit shorter than the e to the x function. Of course, when I plug 1 into the e to the x, I get e. When I plug 1 into the 2 to the x, I only get 2. But I guess the point is, look, here is, again, this point 0, 1. Again, if I kind of squint at this for a few minutes, I realize that this is also a derivative. What is it? It's the derivative of the 2 to the x function at x equals 0. So I can go over here, I can pick a tiny point h, which is a little bit more than 0. I can go up here, label it h comma 2 to the h, and now once again I have this blue secant line, and now I'll just patch that up so it's comprehensible. And once again, I can draw in my tiny little triangle. That's h, and that is 2 to the h minus 1. So I think that's clear. And as h goes to 0, this point h moves infinitely close to the other point of this secant line, the point here at 0, 1. Okay, so whatever the answer to this limit is whatever the derivative of e to the x is at 0. So, all right, every single one of these exponential functions has this exact same pattern to it, and this was also supposed to sort of motivate you to why we had to at some point reach for the sort of precise definition of e, because because in the derivation of in the proof of the derivative of e to the x, we got to this exact same point, and so to make sort of progress, we need to use something that's specific to e. And okay, how do I finish this off now? Well, no one ever does this now, because we are going to do it later, and when we do it later, it's like easy, but if we try to do it now, it's hard. But it is doable. I'm just going to tell you that the answer to this limit is not 1, okay? This is some number that's not 1. In fact, it's a number that's less than 1. And the big sort of takeaway for why mathematicians care so much about the e to the x function is that the derivative of every single exponential function is some constant times that exponential function. But for every other base besides e, that constant is like some ugly gross number. But for the e to the x function specifically, that constant is 1. So in some sense, e to the x is like the real exponential function. All exponential functions increase exponentially. All exponential functions have exponential functions as derivatives. But e to the x is like the pure exponential function, which is precisely increasing at a rate which is equal to itself, whereas every other one has some gross number. What is that gross number? I don't think it's important that I do this for everybody, but if you want to find that number, you're free to do so right now. Take it as like a little challenge, and the challenge is to do the exact same thing that we were just been doing before, right? Let k be 2 to the h minus 1. Observe that as h goes to 0, k goes to 0. Whoops, I might just end up just doing this right now really fast if it only takes me a minute. If k is 2 to the h minus 1, then solve for h. What is h? h is k plus 1 is log base 2 of k plus 1. Rewrite this limit as the limit as k goes to 0 of, now that numerator becomes k, and the denominator h becomes log base 2 k plus 1. So far everything is like exactly the same, logically speaking. In fact, it's the exact same formula. I just have log base 2 here instead of natural log. And does that really change anything? No, it really doesn't. What am I going to do? I'm going to bring that k down. It's going to become 1 over k. I'm going to pop it back up. And if you're still watching, then you can, I think, follow this. And if you don't care, you can zone out for a second. But this becomes 1 over log base 2 of k plus 1 to the 1 over k. And what happens as k goes to 0, that becomes e. And so we get 1 over the log base 2 of the limit as k goes to 0 of 1 plus k to the 1 over k. And that's the thing that we've seen is e. This whole thing is e by definition. I erased it, okay, but whatever, it's there in your mind. And so the answer to this problem is 1 over log base 2 of e. Okay? This shows that e is kind of like lurking here even when we didn't invite it or something. What is this? Well, now this is just like a little precalc b problem. Is this simplifiable? Yes, it is, because there's this thing called the change of base formula, which says that log base 2 of e is just the natural log of e over the natural log of 2. And since the natural log of e of 1 is 1, this is ln 2. Yikes! What have I just proven? I've just proven to you very, very fast. If you don't want to know this now, then who cares? Because it's going to come up later, that in fact the slope of this line is ln 2. And ln 2 is like some number like 0.7 or whatever. Okay, all other exponential functions have gross derivatives. E to the x has a beautiful derivative. That's why we learn that one first. Okay, what's left? We could kind of stop here. There are 2 more things that it's sort of just nice to be able to just have the formulas for right now. And one of them is natural log itself. Okay, the derivative of natural log is calculable, and we can do it right now. Once again, our textbook waits to do it later, but I want to do it now. And okay, let's go. What is the derivative of natural log? Well, again, I guess I'll just start. How do I do this? Well, it's going to be the limit as h goes to 0 of ln x plus h minus ln x all over h. Cha. I use cursive for some reason. Okay, what can I do now? Well, it's pretty good to have some basic facts about logarithms, and maybe I should have reviewed these a half an hour ago, but okay, never too late. You know, how do you teach this to someone who doesn't know anything? You just use some simple numbers.
take, well, what is the log base 2 of 32? Well, the log base 2 of 32 is like the log base 2 of 2 to the 5th. And just by the definition of log base 2 as the inverse of the 2 to the x function, then this is 5, just kind of by definition. So okay, so what is log base 2 asking? It's really asking like how many 2's are being multiplied inside there. And so now if you give me, log base 2 of 8 times 32, say, then it's pretty obvious what the answer is to log base 2 of 8 times 32. On the one hand, there are 1, 2, 3, and then there are 5 2's here and 3 more 2's here. So on the one hand, you can think of this as the log base. You can think of this as the log base 2 of 2 to the 8th, and therefore the answer is just 8. But on the other hand, you can think of this as the log base 2 of 2 cubed times 2 to the 5th. And here, if the log base 2 of a number is just asking how many 2's are in that number, then here's where we get this happy formula that says that that the log of a product is the sum of the logarithms. So here you get log base 2, 2 to the 5th, and that's how you get that this is just 3 plus 5. Okay, so what was this? This was just a very fast, possibly unnecessary for you if you learned this well the first time, not a proof, but explanation of the log rule, which says that the log of any base whatsoever, so maybe I'll just even leave it, I'll just say log, that the log of a times b is log a plus log b. And then the other one is the one with division that says that the log of a divided by b is, just to clarify, that's what I proved over here because, 8 is like my a, 32 is like my b. If I'm asking for, well, that's good enough. And then here we have log of a minus log of b. And then the third rule is the one that says that the log of a to the n is n times the log of a. And the way to convince yourself of this is like, take log base 2 of 8 to the 5th, for example. Well, if you think about what that is saying, it's saying, all right, I want the log base 2 of, let me make sure I do this right, 2 cubed times, times 2 cubed times 2 cubed times 2 cubed times 2 cubed. Well, what is that? Well, it's just going to be, by the product rule, it's just going to be 5 times the log base 2 of 2 cubed. Because I'm going to have, just for that, I'm going to have 5. I'm starting to think this was totally unnecessary, but okay, that was the explanation of the log rules. For you, if you need them. Well, you don't need to understand them, I guess, but you need to have them on the tip of your brain at all times, because now it's sort of just obvious, if you know your log rules well, what to do here in this derivation. And the answer is that this is the limit as h approaches 0 of, well, the log of a minus the log of b is just the log of a over b. So you would hope that this was like a kind of a sort of an immediate idea, and that certainly simplifies things because it makes us have only a single logarithm. Okay, I'm basically just pursuing some kind of mindless sort of algebra moves or something, but maybe they're not mindless. I don't know. Okay, continuing. I can write this as the limit as h goes to 0 of 1 over h times the natural log of x plus h over x. Is there a way to simplify this even further? There is. On the one hand, I can write this as the limit as h goes to 0 of 1 over h times, instead of x plus h over x, I can write it as 1 plus h over x. Now, how sort of good is that or something? I don't know. Something happened. Log of, no.
Everything's good, I guess. Yeah. Good. Sure. 1 plus, yeah. Okay, now what? I guess I can do one more sort of thing, which is to move this h, this 1 over h up to the top. And so here I get the limit, as h goes to 0, of the natural log of 1 plus h over x to the 1 over h. Yeah. And now this is starting to look a lot like E. What is E again? E has two definitions. It's the limit as n goes to 0 of 1 plus 1 over n to the n, and it's also the limit as a goes to 0 of 1 plus a to the 1 over a. So keeping those in the back of our mind, I think I'm almost ready to kind of finish this off, right? Because look, doesn't this look a lot like the thing that I'm trying to do? It does. So let me introduce a new variable. I don't want to reuse, I'll use like b or something. Okay, so what basically I want this h over x thing to be like b. So let b be h over x. And if that's true, then of course h is then just bx. And it's also true that as h goes to 0, b goes to 0. So here I'm just defining a new variable, and I'll now rewrite this limit in terms of this new variable. So instead of being the limit as h goes to 0, since as h goes to 0, b goes to 0, this becomes the limit as h goes to 0 of, as b goes to 0, of the natural log of 1 plus, in place of h over x I put a b, and in place of 1 over h, well h is like bx, so 1 over h is going to be 1 over bx. And now I seem to have like made an achievement, which is I kind of got the x kind of out or something. Alright, I'll just finish this off. This is then the limit as b goes to 0 of the natural log. Now keep in mind that all of this is inside the natural log, right? So this is 1 plus b to the 1 over b, but then the whole thing is like to the x, to the 1 over x. So, but even all of that is still inside, it's inside the natural log. I mean, generally people just write it like this, but they mean that. Okay, what did I do there? I just used exponent rules, right? I just used the fact that that 1 over bx could be thought of as 1 over b times 1 over x, and I just used the exponent rules that say that something to the 1 over b to the 1 over x is just, that's, okay, I think that's clear. Now, I do one more thing, which is to pull that 1 over x down. And I not only pull it down, but I can pull it down from the logarithm, and then I can just pull it right out of the limit, because this is the limit as b goes to 0. And so what I end up with is 1 over x times the limit as b goes to 0 of the natural log of 1 plus b to the 1 over b. And what is 1 plus b to the 1 over b? It is going to e as b goes to 0. So if you want to be even a little bit more technical about this, you can do sort of one more limit law that says this is the natural log of the limit as b goes to 0 of 1 plus b to the 1 over b, and that is just e. So we get 1 over x times ln e, and this is just 1 over x. Okay, this is kind of amazing. This shows that it seemed to be sort of just a bunch of sort of symbol pushing around or something like that, and maybe it was, but this shows something kind of
kind of incredible. This shows that the derivative of the natural log function is just 1 over x. And that, I think, is kind of shocking because this function that I think of as being kind of irrational at every single point somehow has a derivative which is very, very simple. And the answer to this is not actually so shocking if you draw some simple pictures. And I'll draw a simple picture now of the e to the x function. So, this is kind of like the x-axis, and this is like the y-axis. And here I'm going to draw you the e to the x function. And now I'll take a particular point, let me call that point x. And, okay, I'm going to write it as x comma y, but in fact, it's x comma e to the x, because this is the e to the x function. And I'll even just write sort of up here or something, you know, this is the curve y equals e to the x. Alright, and what did I just learn about the e to the x function 10 minutes ago? I've just learned that it's its own derivative. And that means that if we scoot out just like a tiny bit, sorry, I need the space. If we scoot out just like a tiny bit, then we can say how much this function is growing by. And the answer is that for tiny delta x, what is the rate at which this function is growing? It's e to the x times delta x. So the rate of change of this function over some infinitely small interval is always going to be e to the x times, or the increase in y is always going to be whatever the value of the function is at that point times whatever the infinite short amount of time is. That's kind of just what we mean when we say the slope of the by the slope of the tangent line. Okay, great. E to the x and ln x are inverse functions. So if y equals e to the x, then that means x equals ln y. And so, if I want to understand the natural log function, perhaps keeping everything the same, I should try to let this be the sort of y-axis, let y be the sort of input axis now, and x be the output axis, and I'm going to draw in the natural log function, and I'm going to go to the exact same point. This point now is y comma x. And so y comma x I will write. But of course it's also, y is just e to the x. So it's also, let's see, is that what I want to write? No, I guess I want to write y comma, in place of x I'll write ln y. Okay, so that's a sort of arbitrary point on the ln function. But it's the same point y comma x. It's the exact same shape because it's just the inverse function. It's the same shape. And so now, when I get this sort of infinitely small change, I have my triangle going this way. And now, what is this infinitely small change? Well, it's the exact same triangle. So that's still delta x, and this is still e to the x times delta x. But instead of e to the x, I'm going to express it as y. In other words, this change is y times delta x. Okay, and so, what is the slope? I guess this is what I want to write. So I'll just sort of draw this or something, and I'll just say that what we know is that the slope of this line is always just e to the x. But what's the slope of this line? The slope of this line is, well, you tell me, up delta x and over y delta x. So the slope of this line is 1 over y. Okay, I think I might not be explaining this perfectly well, but I think the picture is in fact very clear. It's the fact that the e to the x function is the function that increases at a rate which is exactly itself, which means that the slope of any e to the x function is just like
is just like its y value. In fact, maybe the clearest thing to do is to really say that this slope is just y. So the slope of the tangent line to the e to the x function is just the y coordinate. And so since this is just the inverse function, then its slope is going to be 1 over that y coordinate, because it's just the same triangle, kind of moved, because they're inverse functions. Okay, pausing the video for a second and be back for one more thing.